Hey everyone, we're going to start a new chapter today. We're still going to be studying permutation groups, the symmetric groups and so on, but it is a new chapter, and so it's chapter 9, orbits, cycles, and the alternating groups. And so you can think of this as sort of a deeper analysis of the behavior inside the symmetric groups. So we'll start off like this. So let's let capital A be a set, and I want to take a permutation of that set. So let's call it sigma. Let's let sigma be an element of S of A. So sigma is a permutation of the set A. Now I'm going to define a relation, call it tilde, on on capital A by A tilde B if and only if B is equal to sigma raised to the n of A for some integer little n. Okay, so take a second to digest that right there. So what is it saying? We will say A tilde B, A is related to B, if and only if, by applying the permutation some number of times, and this n can be positive or negative, so it could be the permutation or its inverse. So by applying the permutation some number of times to A, you eventually get B, right? In that situation, then we say A is tilde B, or A is related to B, and it's easy to check, so I'll just say check that tilde is actually an equivalence relation. So this is an equivalence relation on capital A. So what does that mean? Now remember, when you have an equivalence relation, there's a corresponding partition. So as a consequence then, each time we take a sigma, there's a corresponding equivalence relation, which means there's a corresponding partition. So each permutation of capital A induces a partition of capital A. Remember, a partition is just a way of chopping the set up into a bunch of non-overlapping pieces. So each time we have a sigma, some permutation of A, there is a way, it induces a way of chopping that set up into a bunch of non-overlapping pieces. And now for a definition, I guess this is really more a piece of terminology. So let's let sigma be an element of S of A. The equivalence classes of sigma under this particular equivalence relation, so the equivalence classes, of sigma under tilde are, they're called cycles, or no, sorry, not cycles, orbits are called orbits. So let's try some examples. First, let's look at S6. So first example, in S6, let sigma be, so I'm going to write like this, or we'll use our matrix notation to define our permutation. And so I want the second row to be 2, 1, 5. 4, 6, 3. And what I'd like to do is identify the orbits. So remember, the orbits are equivalence classes, so let's just start with 1. Who is the equivalence class of 1? Well, you're going to be equivalent to 1 if by applying sigma a certain number of times, you eventually get to that number. So what happens here? 1 goes to 2, 2 goes to 1. So as you repeatedly apply sigma to 1, it'll go 1, 2, well, sigma of 1 will be 2, then 1, 2, 1, 2. So the orbit corresponding to 1 is the set consisting of the numbers 1 and 2. The orbit of 3. So let's see what happens here. If you apply sigma to 3, you get 5. Apply it again, you get 6. Apply it to 6, you get 3. And then that's going to repeat itself. And so the orbit of 3 is going to be 3, 5, and 6. Then there's one more, the orbit of 4. Notice what happens when you apply sigma to 4, you just keep getting 4, 4, 4, 4, 4, 4. So the orbit of 4 consists of just the number 4. So here's the orbits. And there's a nice little picture that goes along with this. So let's draw it like this. So here's 1 and 2, 3, 5, and 6, and then 4. So as you repeatedly apply sigma, 1 and 2 just cycle back and forth. 1, 2, 1, 2, 1, 2. 3, 5, 6. Just get permuted around. And then 4, well, 4 just keeps going back to 4. Right, so this gives a picture of what sigma does to the numbers 1 through 6. As you continue to apply it, you can see what happens. So let's try another example. We're going to do this in S sub 8. So in S sub 8, let's let tau equal, so we'll do 1, 2, 3, 4, 5, 6, 7, 8, and then the bottom row, 4, 2, 5, 1, 4, 2, 5, 1, 6, 7, 3, 8. Okay, and I'd like to identify the orbits again. So let's look at the orbit of 1. 1 goes to 4, which goes back to 1, which goes to 4. So 1 and 4 just bounce back and forth as you repeatedly apply tau. The orbit of 2, well, that looks like it's just 2. So then the orbit of 3 goes to 5, 5 goes to 6, 6 goes to 7, 7 goes back to 3, so there's the orbit of 3. Who's left? 1, 2, 3, 4, 5, 6, 7, oh, just 8. Okay, and the orbit of 8 is just 8. So if you want to draw the picture of what tau does to the numbers 1 through 8, here we have it. So 1 and 4 cycle back and forth. 2 stays put. 3, 5, 6, and 7, they go around in a little square. So 3, 5, 6, 7, and then 8, let me put it over here, 8 stays put also. Right, so here's a picture of what tau does to the numbers 1 through 8. As you repeatedly apply, 1 through 4 just pop back and forth or bounce back and forth. 3, 5, 6, 7 chase each other around Hopefully I got that in the right order. 3, 5, 6, 7, yeah. And then 2 and 8, nothing happens to them. Okay, so that gives us a picture. And I need to erase this because I'm out of space, but I want to say something about each one of these. So what I really want to observe, we'll take one last look before I erase. Notice what sigma does here. It permutes 1 and 2 in cyclic fashion. It permutes 3, 5, and 6 in cyclic fashion. Tau permutes 1 and 4, and it permutes 3, 5, 6, and 7 in cyclic fashion. It goes around in a circle, if you like. So yeah, let's say that in the first example, sigma permutes the sets 1 and 2 and 3, was it 3, 5, and 6? Yeah, 3, 5, and 6 in cyclic fashion. And that's really, that tells you everything you need to know about how sigma behaves. It permutes this set in cyclic fashion, it permutes this set in cyclic fashion, and anybody that you don't see in that list, which in this case is just 4, gets left alone. In the second example, tau permutes 1 and 4 and 3, 5, 6, 7 in cyclic fashion. So in both cases, in the first case, if I said, all right, I'm thinking of a permutation of sigma that permutes the sets 1 and 2 and the set 3, 5, and 6 in cyclic fashion, that tells you everything you need to know. You would then be able to write down the matrix that gives you the formula for sigma. Same thing for tau. If I said, all right, I'm thinking of a permutation in S8, right? Permutation of the numbers 1 through 8. That permutes the set 1, 4 and the set 3, 5, 6, 7 in cyclic fashion. Everybody else left alone, that would tell you exactly what you need to write down for the formula. Okay. So, definition of permutation sigma in S of n is a cycle. If it has at most one orbit that has more than one element. Is that how I want to say it? Yeah, it has more than one. If it has at most one orbit that has more than one element. Okay, and I guess continue with this definition. So the length of a cycle is the cardinality of the orbit with, I guess I could say that its largest element, a cardinality of its largest orbit of its largest orbit. My previous two examples are not cycles, right? Sigma has a couple of orbits that have more than one element in them. Same with tau, right? So those are not cycles. But let's do an example now. So gamma is going to be given by, this can be an S7. So 1, 2, 3, 4, 5, 6, 7, 4, 2, 3. 7, 5, 6, 1. 7, 5, 6, 1. Okay, so there's gamma, and let's look at the orbits now. So we've got the orbit of 1. That's going to be, well, 1 goes to 4, which goes to 7, which goes back to 1. 2 goes to 2, 3 goes to 3, 5 goes to 5, 6 goes to 6. Ouch! 6 goes to 6. So, well, I guess right now. So, orbit of 2 is 2. Orbit of 3 is 3. Orbit of 5 is 5. And orbit of 6 is 6. And so what does that tell me then? We've got a cycle here of length 3. So gamma is a cycle of length 3. Now, what this is going to allow us to do is to simplify the notation. This matrix notation for permutations is kind of clunky, right? I mean, you're basically having to write out the entire thing. You have to write out the entire domain. And I think, let me just, sorry, I'm going to have to get really close here. I think, oh man. Yeah, my camera's getting, sorry, my camera's getting low, so I'm about to run out of juice, so I'll have to stop this lecture maybe a little earlier than planned. But let's at least get this, what's called cycle notation. So what this is going to allow us to do is to dispense of this sort of clunky notation for defining permutations, and it's going to allow us to get just a more efficient notation for describing elements of the symmetric groups. So, cycle notation. So, let's say that we've got, okay, so let's say if sigma in S of n is a cycle of length, let's say k, right? Then let's say with non-trivial orbit, so with orbit, let's say little I, having more than one element. So remember, sigma is a cycle, which means it has exactly, or at most, one orbit that has more than one element. And so now I want to make sure here, in this case, we've got a cycle that has this orbit that has length, or has an orbit that has more than one element. And so it's the equivalence class of I. Then what we're going to do is write sigma equal to, let's see, in your book, yeah, they put commas in between here, so it'll go like this: I, comma, sigma of I, comma, sigma squared of I, and we go all the way up to sigma to the k minus 1 of I. This is going to be the notation that we use to define sigma. All right? So when we write this, what looks like an ordered k tuple down, what we'll be doing is describing a certain function, a certain permutation of the numbers 1 through n. Okay, so let's jump right to an example. So in the previous example, what do we have? Well, we have this cycle, this cycle gamma right here. And so what do we need? Well, we don't need to know this, right? If it's understood that it's a cycle, then there's going to be exactly one orbit, at most one orbit, that has more than one element. And so if I tell you who the orbit that has more than one element is, that's all you need to know. So in the previous example, we could write gamma equals 1, sigma of 1 is 4, sigma of 4, which is sigma squared of 1, is 7. And so this tells us gamma is a cycle. It takes 1 to 4. It takes 4 to 7. It takes 7 back to 1. That's how you interpret this. And if you don't see a number in here, nothing happens to it. All right? So it gives us much more efficient notation than this cycle notation, or this matrix notation that we were using. So we're going to stop using this matrix notation pretty soon once we get a complete definition or description of how to define a general permutation. Now I should point out, it's understood that everything can be permuted cyclically, right? So the orbit of 1 is the orbit of 4, which is the orbit of 7. And so this is not a unique notation. If I wanted to think, well, let's think in terms of the order of 4. 4 goes to 7, which goes to 1. This describes exactly the same permutation. And one more way we could write this, 7 goes to 1, which goes to 4. So you can permute these elements in a cyclic fashion and you'll get the same formula, or it'll describe the same function. Okay, so let's try another example. I don't need to say in, so let's just call it beta. So beta is 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is an element of S sub 8, and 1, 4, 3, 6, 5, 8. 7, 2. Okay, so let's figure out the orbits. The orbit of 1 has a single element. The orbit of 2, so the orbit of 2 is, let's see, so 2 goes to 4, 4 goes to 6, 6 goes to 8, and 8 goes back to 2. And then let's see, what else do we have? So 1 goes to 1, 3 goes to 3, 5 goes to 5, 7 goes to 7. And so beta can be written as 2, 4, 6, 8. That's not the only way to do it. We can permute things cyclically. So as long as we say, so for example, 8 goes to 2, which goes to 4, which goes to 6, which goes back to 8. So I'll just say etc. Right? There's 4 different ways to write that one. I guess let me check how much juice is left in my camera here. 13%. Oh, I think I can squeeze a little bit more out. Okay, so let's do, I want to make one more comment and then do one more example, and then I guess we'll have to quit a little bit early. But here's the thing to notice. Cycles are permutations, which means that they're elements of the symmetric group, and we can multiply elements in the symmetric group. So since cycles are permutations, we can multiply them. Right, so we can multiply them. And remember what that means then, right? Multiplication in the symmetric group is composition. So compose them. Okay, so let's look at an example in S sub 9. S sub 9. let's get a couple of cycles. I'm going to call them mu and nu. So let's let mu be the cycle 2, 4, 7, 8. And nu is going to be the cycle 1, 2, 5, 7, 9. Okay, so now what I'd like to do is multiply these, and remember, multiplication means composition. In composition, you read right to left. So, so for example, I'll just do a few computations here. So let's do mu nu of 1. Well, do nu first. So nu of 1 equals 2. Mu of 2 equals 4, and so we get 4. Mu nu of 4. Nu of 4 equals 7. Mu of 7 equals 9. Mu nu, I'm going to do a bunch of examples here. So, oh, I actually computed. Sorry, I did this out of order. I actually want to do all possible computations here. So I'm going to do 2 through 9. So mu nu of 2. Nu of 2 equals 4. And then nu, oh, I said that backwards. Sorry. Nu of 2, let's just hope I didn't screw that up. Yeah, okay. So yeah, nu of 2 equals 5. Mu of 5 equals 5. So what we get is 5. Mu nu of 3. Okay, so first do nu. Nu of 3 equals 3. Mu of 3 equals 3. And so we get 3 all the way across the board. Okay, so now how about 4? First do nu. Nu of 4 equals 4. Mu of 4 equals 7, so we get 7. Mu nu of 5. 5 goes to 7, which goes to 8. Okay, so now we're going to apply it to 6. So 6 goes to 6, which goes to 6. Now let's plug in 7. So first do nu. 7 goes to 9. 9 goes to 9, so we get a 9. Mu nu of 8. 8 goes to 8, which goes to 2. And then the last one, mu nu of 9 equals, so let's see, 9 goes to 1, which goes to 1, and so we get a 1. As an exercise, compute nu mu of I for each I between 1 and 9. Okay, so what you notice now is we took two cycles, we multiplied them together, and that gave us a permutation, which, by the way, this particular product is not a cycle. It gave us some other permutation. So we've defined this thing called cycle. Not every permutation is a cycle, but by multiplying cycles, we got other permutations. And so that's going to be the idea, is that cycles are going to be the building blocks of permutations in general. Okay, so that's a good place to stop since I'm out of juice on my camera. We'll pick up later and continue this discussion, right? Learning how to multiply cycles and how that's significant when we're working inside S sub n. Okay, so see you later.